So now we're going to go on to the book overview. Chapter 1 is the introduction, and as an introduction, I was able to kind of include some of these things on product and systems, just because they didn't really fit into some of the other chapters. So there's a couple of things that we just have up front that frame things. Chapter 2 is how to learn LabVIEW FPGA. And so I've trained a lot of people, I've consulted a lot of people, and I've worked on teams. So I've seen what people struggle with when they're learning LabVIEW FPGA. One of the big things that they struggle with is they're going from a software mindset to a hardware mindset. And as they're doing that change, there's things that they either need to learn, or I don't want to say unlearn, because you still need to know those things, but you need to be able to sort of, and I don't like the term paradigm shift, but it really is a paradigm shift. You're kind of shifting over from this mindset to a different mindset. Also, the book has this diagram. Let's get us to zoom in. So I have this diagram, this sort of a learning path, and because as I thought to myself, there's all these different users, and even though there's different users, in the end, they still have to go through the same learning path. Because I also thought to myself, if I had to make a learning path for each different type of user, that would get really complicated. So and actually I did do that initially, and as I started to kind of make this sort of like what's the learning path, I started to see some similarities. So I kind of worked on it a little bit more and came up with, here's sort of this workflow. Everyone goes through this approach. So the first thing, of course, you may know this already, you gotta have a problem to solve. You could read all the books and resources in the world. If you don't know of a problem or an example that, something that you need to do, it's all just going to be information that's unhinged. You're not going to know what to do with it and where to connect it. So that problem to solve, hopefully you're doing some kind of requirements development, whether they're structured or not. But as things are coming into your discussion, you capture them, you have some kind of requirements. Also, we need to know, so part of that is maybe there's application needs. You're building a solution. In some cases, maybe you're just building some tools. So these are more like utilities. Maybe they seem to be simpler in nature. We're not so focused on the user experience, but we're just focused on a certain capability. And then moving down to this sort of middle area, this is sort of our software area. So some kind of software knowledge is important. And that's because the software is going to be used to make a software model. It's going to model the way the FPGA is going to work. The software is also going to be used, software knowledge will also be used to make the host to FPGA interface. So that's the API or the interface, however it's going to communicate to the FPGA. So, and by the way, all these things that I'm showing here, one person doesn't need to know all that. I mean, it's great if one person knows all that, but these are skills that the whole team, right? So speaking to the managers, you're building a team, these are all the different pieces of expertise, right? You don't get people that just know everything. So not one person needs to know all this. So the middle part here, software knowledge, we start out with generic software knowledge, meaning that it could be any software, right? It could be C, it could be Python, it could be MATLAB, LabVIEW. And of course, part of software knowledge, you should know some software engineering tools and processes, some of the tools we talked about earlier. And then we go down, and if the software tool that we knew wasn't LabVIEW, we do need to know some LabVIEW. Even if what you're deploying is going to be in a C environment, or it's going to be, it's going to interface, it's not going to interface to LabVIEW, you still need to know LabVIEW because LabVIEW FPGA uses the LabVIEW environment. So you need to know, the block diagram and front panel and just all those concepts. You need to know those. There's no way around that. And then there's of course LabVIEW proficiency, where you can work on multi-person projects and larger projects. Those are ways that, at least for me, if someone says to me that they've been using a lot of LabVIEW, if they worked on larger teams, if they've worked on larger projects, that certainly is one indication as to how much LabVIEW proficiency they have. As opposed to someone who's always worked on just single person projects, they may not know as much about modularity or communication between the different team members and being able to sort of design things out. That's sort of kind of like with the product mindset that we mentioned earlier. And then now we move down to the hardware side. So some kind of FPGA knowledge is important. And again, the whole point of LabVIEW FPGA is to not know that much, but some of it does need to be known. You get your first compile failure, guess what? You're learning FPGA concepts. So sooner or later, you're going to have to know about FPGAs. And then, of course, we've got LabVIEW FPGA proficiency, which could be, handshaking and pipelining and maybe integrating outside IP or working with multiple FPGAs. So LabVIEW FPGA proficiency, which the book goes into a lot of that. So there's a whole bunch of things that could be considered LabVIEW. You've got LabVIEW user, just knows kind of the environment. And then we've got someone who's really proficient in it and has a good amount of expertise. Okay. Let's zoom out. And also chapter 2 talks about the different kinds of users. Actually do identify them, even though regardless, you're going to go through this path that I mentioned. And I guess one last thing, as far as learning LabVIEW FPGA, sometimes, maybe more often than it should, I find people that are struggling to learn LabVIEW FPGA. And it's not because they don't have the right aptitude or something else, or the background. It's because they didn't follow this path. I've traced it back to that and say, oh, you kind of skipped this piece. You don't have a software model. Oh, you don't have a problem to solve. You don't, or the problem isn't really defined. Well, I'm just trying to create something. You got to sort of go back and they're not using software tools, some of these software engineering tools. So sometimes the problem lies in one of these stages being essentially skipped or conflated, right? Like they tried to learn everything all in one shot. Chapter 3 is the background technology chapter, which we did talk a little bit about earlier. So now, because FPGAs are an obscure technology, I find it beneficial to talk about FPGAs from different points of view. I find that talking about the history of FPGAs is beneficial because you get to see how they came together. In other words, current FPGAs can have thousands of DSP slices. They can have hundreds of thousands of lookup tables and flip-flops. And I mean, they're really complex. So sometimes looking at the first FPGA had 64 logic blocks. It was arranged in an 8x8. Came out in the 84, 86, somewhere around there, mid-80s. You look at how that worked. Maybe that's a better place to start, and you kind of see, and then maybe you follow the evolution. The book we follow the evolution. We say, okay, well, first they were doing glue logic, and then they were being used to do some more DSP. They were being used in telecom, and then they started to be used. They started to put more complex DSP. Then we had high-level synthesis tools, and the development environments got more mature. And then we've got system on chip and overlays, right? So following that history certainly gives you some context. Then, of course, we look at what's going on inside the FPGA, which we did talk about earlier, all the different blocks that are in there. And going inside the FPGA can be a big rabbit hole, right? I mean, you just go on Xilinx's website, which is one of the companies that makes FPGAs. And just for a single FPGA part, there's all kinds of documents and 50 to 100 page or 200 page PDFs on not just one FPGA, just on all the things that are inside that one FPGA. So you got to be careful with not to get too distracted with that, or to make sure you're learning the right information. We then look at the benefits of FPGAs, right? And the benefits of FPGAs are you've got the ability to have high throughput. So large amounts of data flowing through a system that you can then either reduce or trigger off of or modify or be able to process large amounts of data, gigabytes and in some cases terabytes of data per second. And FPGAs can be used for low latency applications where you need to have a quick response, right? So a radar pulse is coming in and you need to be able to respond to that, or some other signal is coming in, you're trying to detect things in the spectrum. The FPGA can be very beneficial for that. Another way of understanding FPGAs is to look at the industries and the applications, right? So this subsection goes beyond RF, radar, and electronic warfare, and it looks at industries such as medical industry. Medical devices use FPGAs. Pharmaceutical industry uses them to do genome and sequencing of different patterns. Some are even using it to mine cryptocurrency, right? So but it's also used in data centers. It's used in financial applications, high frequency trading, dealing with a lot of data, and certainly, any kind of self-driving cars are using FPGAs. So even though FPGAs on the surface, they appear to be obscure and sort of mysterious, they're used in a lot of places, and in places that in our day-to-day lives, right? Like the car you're driving that may have adaptive cruise control, or a lot of cars do have radar. There's an FPGA was certainly involved somewhere in that process. If not in the solution, it was probably used to test it. And then we end with a comparison of FPGAs to GPUs, CPUs, and ASICs. And that helps, again, I think you approach it from different points of view and don't go too deep on each of those. I mean, certainly there's lots of further reading references mentioned in the book that you want to learn more about a specific topic that I mentioned. You can certainly go down that path. Chapter 4 is using LabVIEW FPGA. And some would think that the whole book should just be chapter 4. But there's LabVIEW FPGA's got a help file, right? It's got documentation. There's application notes on NI's site. There's a discussion forum. So I certainly didn't want to replicate all that. I mean, that's already written. So that's why putting together some of the things that we talked about earlier, and then looking at how some of these things come together. So first off, I talk a little bit about the LabVIEW environment, but I tried to not have too much info in that sense, just because there's a lot of other, I didn't want to duplicate what exists out there, right? So for example, there is a LabVIEW for graphical programming book that just came out last year. So it's the 5th edition of the book. It was actually, the 1st edition was my first LabVIEW book. So a book like that pairs really well with this book like this. And the generic LabVIEW FPGA system view, I'll show that in the next slide. We talk about the host interface and the ways that you communicate with the FPGA, whether it's with FIFOs or with registers or with the instruction framework. And then we look inside the FPGA. What's happening in there, the clocks, the different IP options that we have, and just how all of that gets configured and how we optimize the FPGA. We spend some time talking about simulation mode and the importance of it and just how we can use that. We talk about compiling, and we talk about different types of compile failures, different ways of working around those compile failures, things that we can do to get that solution working. And then debugging, right? The FPGA, once it's compiled, it's running on a chip. How do we debug that? What are the different techniques that can be used for either pulling data off of the FPGA or things like that? Another important aspect of LabVIEW FPGA are export options. So for example, we can export the IP as of 2020, but I also do talk about the Vivado Export, which is a way of taking your, Vivado is the development environment that Xilinx makes, the manufacturer of FPGAs that NI uses. So now you can take your LabVIEW FPGA environment and export that into a Vivado project. And so that gives you more control, more options in terms of making your compile more efficient. And you're just in a more native FPGA development environment. Okay, I'm going to zoom in on this, don't worry. So the generic LabVIEW FPGA system view. So this is a diagram that, if we go through all the different things that interface or communicate to an FPGA, LabVIEW FPGA-based system, this is what you get. So it's the superset of all the interfaces. And by the way, remember before we were talking about systems approach, the interfaces? These are the interfaces. Now, if we were to zoom in, here we've got the FPGA in the middle, and we can see the different ways and things that exist that we can interface the FPGA to. First of all, here we've got the host. Here we've got the PXI bus. We've got our FPGA board. We've got other FPGA boards or instruments. And then just the outside the chassis or outside of that. So on the host, we've got our, even writing the disk is critical because you've got record playback systems in the RF world, which are critical. We've got the host interface, whether it's a GUI or an API that's being delivered, and that can interface with DMA FIFOs or controls and indicators. And then there's instrument design libraries. And then we've got our device drivers that are allow us to interface to some of these instruments, right? So these are all the things that will typically be happening on the host. On the FPGA itself, we've got timing and synchronization that communicates with the PXI bus. And here we've got off-chip but onboard memory called it's DRAM, and we can write and read to that, of course. Then down here we've got our peer-to-peer writing and reading. So that allows us to communicate with other FPGA boards or instruments. We've got our socketed clip that allows us to communicate with the outside world, so with I/O. And we've got our multi-gigabit transceivers, which is that's the physical interface, which allows for high throughput, low latency interfacing between the FPGA and other devices, other FPGA devices, or it can be used to communicate with a network device such as a network attached storage or a network server. You can kind of stream that data back to some kind of storage. So instead of having to go back over the host, we can just write from the FPGA, we can go right to some kind of storage. And then here we see the other instrument. So essentially, and part of this chapter is taking, it gives you sort of this big picture, right? Like what I found is that a diagram like this doesn't exist anywhere, or nothing with all this information. And so bringing that all together, breaking down each of these pieces, and how are you going to use them is what we do in this in chapter 4. Chapter 5, we look at RF LabVIEW FPGA case studies. We talk a little bit about the problem that's being solved. We talk about how the NI platform can sort of, how it gets applied to that, and some of the common NI FPGA architectures, whether it's using PXI or maybe it's using the ATCA, or maybe it's going to be using like the EDIS software-defined radios. And then we break all of those pieces down into components. And so the idea is that there's some of these things, they're proprietary, or they don't go into there's so many ways that they can be used. So rather than talk about one application or another, and we look at all the components or the typical components that go into an RF test system. And the idea is that if you know what those RF components are, you've got these common architectures, you can sort of get these different pieces and put them together to build your system. And as far as specific case studies, there's a couple of other LabVIEW FPGA case studies that are mentioned in the book. But then here we talk about specifically the NI VST, because the VST, even though it's a product, in and of itself, the VST is, I consider that to be a case study. Because you have something that is fairly complex. It's something that has a host interface that is interfacing to it's got the RF interface, the RF driver that NI has for the VST is a mature driver, right? It's not something that's just peeking and poking to the FPGA. Another one that we look at is the real-time spectrum analyzer, which is something that's available from NI's website. And by the way, the VST and the RTSAs, some of the VST code is available, the first generation, so I do show screenshots from that, and I can talk more openly about that. But the second generation VST NI makes it available on demand, on request rather. And so I can't show specifics on that just because it's not something that NI is makes it publicly available for everyone. But I certainly do talk about some of the techniques that are observed being used in the VST and the RTSA, and things that sometimes people, they don't need to know exactly what that thing does, but they want to know what's possible. And so speaking to what's possible and what the capabilities are, then you can kind of get an idea of what you can do with your hardware. And then another critical RF case study is we talk about phased array systems. So that's chapter 5. And on the diagrams that we can see here, if we were to make a phased array system, we could have multiple synchronized VSTs on the same chassis. So that's a critical aspect of it's a multiple input, multiple output system, MIMO. It's one of the configurations you could use for that. And then above that is a screenshot from the NI RTSA. And the RTSA is doing hundreds of thousands of FFTs per second. So and that's running on a Kintex 7, and that it can run on some of the newer ones, but it's quite impressive. These are also examples of speak to the maturity of LabVIEW FPGA itself. So this book is coming out this month, and things are always changing, right? So let's put it this way: from when I finished writing this book to now, Xilinx, the company that makes the FPGAs that NI uses, has been acquired by AMD. The book doesn't reflect that, right? Because we were finished with any edits. We're not making any more changes. But if you just think about that, I mean, that's a major change. So things are going to keep changing. So just whatever's in the book, certainly it gives you a pretty good starting point. But you need to keep sharp. You need to keep, following the developments, whether they're, if you're a radar engineer, you want to follow the different techniques, the way people are doing like cognitive radar and that sort of thing. And on the FPGA side or the LabVIEW side, you do need to follow what's changing, what's happening. And so here you can see I'm looking at not just, and that's another thing. The book this chapter does have a section on LabVIEW NXG, which is development for NXG has been ceased. So as much as I try to make things, up to date, things are changing, right? It's a dynamic world that we live in. So what I did was, in terms of putting together this chapter, because I always consider it's important for you to stay current. What I did was I looked at, there's a term that's used, it's called the technology readiness level, TRL. And it's a scale, I think NASA came up with it, or the DoD. And you kind of start with like 0 or 1, and then it goes up to 7 or 10. I don't know, it depends on which scale you're using. But the point is, as a concept, the TRL tells you how mature something is for usage. So for example, back in the 60s, you have the early days of the space program, certain technologies could only, they were so advanced and complex and expensive that only NASA could use them. And meanwhile, we know, that our cell phones, our computers are using technology from that era that is now commercialized, right? Like everyone's got one of these devices in their back pocket. So for that to happen, the technology had to move up the TRL, the technology readiness level. So for me, I looked at things that are lower or earlier on the TRL and said, well, and then I made some predictions or just some guesses. And as we know, most of these predictions, we don't know if they're going to be right, but it's kind of fun to imagine a little bit and kind of try to think ahead what may happen. The first one is Fpga Overlays, and I've got a slide right after this that we're going to go into, talk about overlays. The second one, SoC, System on Chip. Now, if you look at the different developments of what's happening, you've got Intel acquiring Altera. You've got AMD acquiring Xilinx. You've got NVIDIA acquiring, what's that other company? ARM. They bought ARM. They bought Mellanox. Right? There's different companies. I think Xilinx bought SolarFlare. Right? So there's a consolidation. There's sort of all these companies are sort of merging, which maybe as engineers we're not fans of that because the companies lose their personality when that happens. But it's happening, right? It's a fact. And so what's really happening? That's happening on the business level. There's this sort of integration. But what's happening on the other hand is we used to have what's called the approach was homogeneous computing. So you need computing. Okay, here's a whole bunch of CPUs, and they will do your computing. Or here's a whole bunch of GPUs, and they will do your computing. And some people also use FPGAs for their computing, whatever it is. But the idea is that where the move, and it's not new, right? The move for the many years now has been towards heterogeneous computing. And so this means that you have, again, the right tool for the right job. You want to process this kind of data. Maybe you want to process network data that's coming in. Well, you're going to use this kind of a processor for that. Then the data comes in and gets processed. You're going to use some other processor for that. And so whether they're distributed components or they're all integrated, system on chip. And system on chip isn't really formally defined anywhere. But system on chip is something that you're seeing more and more of. And that doesn't mean that it's going to replace CPUs and GPUs and FPGAs. We actually don't know, right? Like, so we're at an interesting time right now. So there's a lot of things that are happening. You can see, I do reference in the book, I reference the Hot Chips conference, which is an IEEE conference where you could see Amazon and Microsoft and Google all trying different ways. Maybe they're more than trying. They've implemented different ways of using these technologies. So my favorite one is Microsoft's use of FPGAs to accelerate web search, the search engine Bing, and Azure. You know, like they're using it behind the scenes to do things that, you know, people would have thought, well, FPGAs can't do that. 15, 20 years ago, few people could have imagined that possible. Now, the system on chip leads us to something called domain-specific architectures. So we've got CPUs and we've got GPUs. GPU is kind of domain-specific, right? It's graphics. That's a domain. But what if we had, and I kind of make these guesses, and I say, well, what if we had a radar processing unit? Or what if I had a processing unit that has a lot of those pieces built into that? And actually, there exists such a, I couldn't find the term radar processing unit out there, but Xilinx does make an RF SoC. So it's a SoC, system on chip, that focuses on RF. And so essentially, that's what you can see here. That's this image that you see on the right. It's got built-in A to Ds and D to As. It has CPU built in. It's got ARM CPUs in there. It's got floating point processing built in, right? Historically, FPGAs, they would say, well, they can't do floating point. Well, with a SoC, you can. You can just kind of integrate that all together. It's got connectivity. You can see gigabit Ethernet, CAN bus, SPI, all kinds of different interfacing, USB, PCI Express, DisplayPort, right? All that is in the system. And the idea is that, you know, a company like Xilinx, to make something called an RF SoC, they know that there's enough need, there must be enough need out there for them to make something that has all of that ability. In fact, the other day, I just saw something that Intel, you know, of course, it's what used to be Altera, the division that used to be Altera. They also have something that goes, I think, 60 gigabits per second, gigasamples per second, or 64 gigasamples per second. You know, it's an interesting time for some of these for the semiconductor world. Fourth bullet over there, FPGA platforms is so clearly I'm a LabVIEW FPGA user. The book is certainly talking about this platform, but I try to take. I don't want to just come off as, well, I'm a fan of it. I just like it because I like it. I try to break down. I mean, I like it because it's graphical, and, you know, there's a whole bunch of reasons. But I tried to break down what are the things that, from a business point of view and technology point of view, what makes a good FPGA platform? What is that criteria? And so I look at, does the FPGA platform use the latest FPGAs? Are they changing? Are they evolving? You know, so that is happening. Are you able to integrate outside IP? And a couple of other things. So those are the things that I outline criteria for what makes a good FPGA platform. And it's in no way am I implying that, you know, let's say NI is not going to do this in the future. You know, they certainly seem committed. I can't predict the future, but they certainly seem very committed to keeping their FPGA platform up to date and using, you know, they're using UltraScale Plus FPGAs besides UltraScale, and, you know, they've been using pretty much, they have products that support pretty much all the generations that I've been seeing, like different families of FPGAs that support Zinc, which is one of the RF SoCs. Sorry, not RF SoC. It's one of the SoCs. So we try to take a look at the bigger picture in that sense. And some would argue it's also taking a more academic approach, not a commercial view of what is an FPGA platform. Just think of it just its basics. RISC-V, that's how we pronounce that, right? That's not RISC-V. RISC is the reduced instruction set, right? Something that some of you may have heard about in your college classes, or you just know about that from computing. There's RISC and CISC. So anyway, RISC-V is a relatively new development. It's a couple of years now. There's a RISC-V Foundation, and RISC-V is a, so now when you use a Intel processor or an AMD processor, you're using the instruction set is, the ISA is the interface, is proprietary. It's specific to Intel, or it's specific to AMD, or it's specific to whoever is making that processor. What RISC-V does is it defines that interface, that instruction set. And so the idea is that when you're going with a specific vendor, it's kind of open sourcing processors in a way. But as with open source tools or OSs like Linux, there's still a business model. So there's companies that are taking the RISC-V architecture and they're making processors. And so we can imagine like who this is. This is, there's different targets on that, where it's different kinds of semiconductor manufacturers that this is taking aim at, which is to be seen. But if we were to look at the different members of the RISC-V Foundation, you can see who's on there. There's different companies. There's some defense contractors. There's semiconductor manufacturers. There's board manufacturers. So it's kind of it's an interesting mix of companies that are members of the RISC-V Foundation. And so based on that, that certainly gives us a sense of like what may happen in the future, what they're developing. So FPGAs take us to SOCs, and then SOCs takes us to CPUs. So it's kind of, they're all related now, right? In the past, we would have had an FPGA discussion and it would just be digital design. So here it's a lot broader. Another section I included in there was echolocation in nature. If you look at some of the latest in radar and RF, they talk about things like cognitive radar, where they're looking at how the brain works and taking some of those concepts and applying them to radar. So looking at echolocation, which I know that's echolocation implies sound. We don't have any RF animals out there, but we have. But the concepts are very similar, right? They're sending out some kind of a pulse or some kind of a signal, and the way a bat flies, for example, or detects what's around it. It's very similar in terms of the concepts. And so looking at some of those techniques and looking at some of the way these things work, you can get ideas as to things that could go and get fitted into these. They can get fitted into, they can be used in future projects or future applications. Things that I found really interesting on echolocation was the way that, if you think about the complexity, a bat that's flying, bats can't see, and a bat that's flying and can catch an insect in the air while it's flying. You can imagine that it's acquiring a target that's moving while it's moving, and maybe there's wind and there's a whole bunch of things. And it's a really complex system. That's what's happening there. And then, of course, there's dolphins and there's different animals that have this ability. I also found it interesting that even humans that have seeing impaired, they are able to develop. I think they even develop echolocation. Some humans are able to develop that because it's just, and we know that their sound abilities get better, their hearing abilities get improved to cover for the loss of sight. So certainly there are things in here that we can. They certainly will make their way into the technology. And then the last part of this chapter is staying current, where we talk about, I mentioned different conferences, different magazines, different journals, websites, and things that I follow currently. And again, these things are going to change, but it's really an important thing. And so now the next slide is going to be a little bit about FPGA overlays. And I think out of everything that's here, FPGA overlays, they're here now. So there's two examples that I have here. One's going to be Pink, which is basically Python working with Xilinx Zinc, like they're kind of combining Python and Zinc. So when we have the way an FPGA workflow works today, everything seemingly is very custom and purpose built. So you have someone that goes and works on the FPGA, someone works on the software, and then they just put those together. And then if we want to make a different system, someone has to go make another FPGA and someone makes another host interface and we put those together. Now, as the problems are sort of becoming better understood, the idea of an FPGA overlay is that you have an FPGA configuration, some people call it the FPGA personality, that it has various ways that it can be controlled and modified. So that's the hardware part. That's the pink overlays that you see at the bottom. So again, this is using Python, it's open source. You got these bit streams down here at the bottom. Then we've got the driver that interfaces to it. And then at the higher level, you've got Python, and then something that's even above that, you've got the applications. And so the idea is that if the idea is that you can have, if the FPGA has the right amount of registers and interfaces exposed, we can do quite a few things without having to rebuild the FPGA. So you get something that's a purpose-built, it's a domain-specific architecture in the FPGA, and then software people at the Python level can work with it. And then, so certainly once in a while, we'd have to change the FPGA so we could reprogram that. And then, certainly there's a bigger change there. We'd have to wait for a recompile. But the idea is that because the bitstream exposes a whole bunch of things that you can change, and again, once you get into maybe like a radar application or an electronic warfare application, we know that it's not going to be processing genome data, right? Like we know that it's going to work a certain way. You're going to have maybe like a certain repetition that's going to have like the pulse rate, or you're going to have different kinds of DSP that's going to have to be in there. So we kind of know those things that are going to have to go on there. So we can maybe build those in, but just make things more configurable so they could work from the host side without having to reconfigure it. So that's happening on the Python side. Now, the NI VST, I couldn't find this term anywhere. Like I didn't see NI referring to it as an overlay. But for me, it is an overlay. If you look at the definition of an overlay and how you have something that's really configurable, it's got a software interface that someone can change things and do things. It's one of those things where it looks like an overlay, it sounds like an overlay. It's an overlay. And so within a VST, you've got this like RFSA and RFSG driver that can control the VST. And then on the VST, it has a whole bunch of blocks that are sort of in there, but we can change those from the host. But the VST itself can be changed. And so when that changes, certainly we want to make sure that the host interface doesn't break, but then we may have to extend that or add to it. So in that sense, it very much is an overlay. And I think that as we understand the problems better that are being solved, we can have, overlays will be a thing. In fact, one of the books that I used as a resource, a good resource, was talking about FPGAs for software engineers, or software engineering, software for FPGAs. And there's a whole section. It's got like sections and then chapters, groups of chapters. There's a whole section. So it's got like 3 or 4 chapters just on overlays. So it's a thing, right? Like I didn't just find a couple of instances of it. And that's the end of the book part. There's one more part. I'm looking at the time. I think I'm going to try to keep some of this stuff short, the last part. The book will also have a companion website. So some of these resources, some of the things that we've been talking about will be on there. You can, I know that going through a paper printed book and trying to type out like a YouTube playlist is not fun. So the idea is going to be that a lot of the references, we're going to have them on the companion website. It's going to be on GitHub. It's on there. There's at this moment, if you go there, there's nothing on there. So, but you can go there and like a lot of the references will be put there. So that way you don't have to, if you're on a section and you want to see, okay, what's code that goes with this, or maybe what's a good reference for this? Where do I go? How do I go to that reference? I'll have that there. So you saves you on the clicking and all that stuff. Okay. So that's the overview of the book, and the The last part is kind of getting started on your LabVIEW FPGA project, and some of this will be on the companion website. It outlines a list of questions that I ask and discussion topics. So when I first start to work with someone, whether it's an individual or a team, I'm just training them, or I'm consulting them, or I'm actually going to be part of their team, like integrated, and we're working with them. There's a whole bunch of questions that I ask that helps me understand their background, their experiences, the project. Is the project new? Is it a revamping of the project? Is it a legacy project that we're replacing it? We try to look at the different, like, where are they in their learning, right? I worked with a group one time where they certainly seemed like they used a lot of LabVIEW FPGA, but then as I started to ask questions, they didn't know everything. Nobody does, but there were certain parts that I thought they may have known, but they didn't. And so there's a list of questions that I have that it's really like it's kind of a self-audit. You kind of look at the bottom part here where I ask a bunch of questions about your LabVIEW project. I ask a bunch of questions about the development team and the way they work. There's a bunch of LabVIEW FPGA questions that I ask. And these are really just for self-assessment, right? These aren't really to say, well, you don't know this, or you don't. You kind of need to know how much you know, so that way you can fill in those gaps. And of course, there's a reference to me, it's a very important resource. It's the NI Center of Excellence. So that's a certification that you can get from NI, and whether or not you want to get that or need that certification, it still is a really good resource. So you can go on there, and it has a lot of these some of the self audits. They're inspired by some of the questions that they ask there. It's kind of based on that. I kind of expanded on that, and then it also has a lot of guides and a lot of like free presentations and videos. So it's a really good resource. So that brings us to the end of the presentation. I want to thank you. Thanks all of you that were on here. Here's we've got the link for the book. It's on Artec House's website. The book companion link, my LinkedIn. Certainly feel free to keep in touch. A couple of people have connected with me as a result of the book coming out, which is really neat to see people who are using LabVIEW FPGA. And so at this point, if there's a chat section for the next half an hour or so. Maybe you've heard enough. You're tired. But if you do have questions, I could go for another 8 hours, right? I'm just getting started here. But if you have any questions, feel free to put them in the chat of Microsoft Teams, and I'll do my best to answer them.